What is going on here? We have the integral of x to the negative x equals the sum of n to the negative n, where we're going from 0 to 1 in this case, and n equals 1 to infinity in the discrete case, right? Discrete case, continuous case. So how do you calculate this? Well, let's go ahead and calculate it. Okay, so how do we calculate all of this? Well, our first step is going to be to take x to the negative x and write it as e to the log x to the negative x. And then I can pull this negative x to the front to get e to the negative x log of x. So this thing is the same thing as this. Now, e to the power of z, you just put the z in here to this formula for the power series. So what's the power series of this thing? Well, what we're going to end up with is a power series from n equals 0 to infinity, where I just replace the z here with negative x log x. This z gets replaced with negative x log x, all to the power of n, all over n factorial, and we've got the dx, like so. Our next step is that we would like to interchange these integrals. Now, yes, I am calling this an integral because from a certain point of view it is an integral. It's just with respect to a different kind of measure than this one is, right? So I'd like to interchange those two integrals, but you can't always do that and have things, it's not always going to give you the same result when you interchange them. In this case, though, it will give the same result. So the first thing, let me just explain how this works. So if I have this with, something here, I'm not going to go into technical detail, but I want to take the absolute value of whatever it is, so I would take the absolute value of this. But fortunately, this thing is always positive because this x is between 0 and 1, and log of something between 0 and 1 is going to be negative. So when I take that negative thing and multiply it with a negative, it becomes positive. So taking the absolute value of this leaves it the same. Good. Now, if we calculate that this thing is less than infinity, or we calculate that the other one is less than infinity, so if we can prove either one of these things, then we will be justified switching those integral signs, which I won't go into technical detail about all of that, but I'll definitely include a reference. So what I'm going to do is I went ahead and changed the order of the integrals, and we'll just calculate this, and at the end we will find that it is less than infinity, which will then mean that this thing is the same as doing it the other way around. Okay, so we just have to calculate this integral. And it's not too bad, so we'll just do x equals e to the negative u. That's the substitution I'll make. If you did positive u, I think it would be fine. You would just have to do a negative substitution at some point, like x equals negative, or u equals negative z. This will be just easier for us, so we'll go ahead and take the derivative of both sides, like so. And we'll go ahead and just plug all of that in. So let's just focus on this part, actually the integral part as well. So I'm leaving out the sum sign. So if x is 0, then u would be infinity, right? If you plug in infinity here, you would get x equals 0 over here. So x equals 0 becomes u equals infinity, and x equals 1 becomes u equals 0, like that. Then I'm going to have my parentheses. I'm going to have negative e to the negative u there. Log of e to the negative u is just negative u, like that. These negative signs are going to go ahead and cancel each other out. I'm going to be over n factorial, of course. And then the dx is going to become negative e to the negative u du. So I'm going to multiply this by negative e to the negative u du. I can make this a positive sign, so I'm making the whole thing positive. That way I can go ahead and interchange these in the order of integration, like this, 0 to infinity. Looks a bit nicer. And then I'm going to have the integral of e 0 to infinity. So e to the negative u to the power of n. Let me write it up here real quick. E to the negative u to the power of n is going to give me e to the negative u times n, and then I'm multiplying that by e to the negative u, like this. So this negative u is multiplied by 1, so I'm going to add these exponents together. N plus 1 is what I'm going to get. So I'm going to get e to the negative u times n plus 1, like that. And then u to the power of n, that's easy. That's just u to the power of n, and we've got the du, and we're all over n factorial. Something quite nice is going to happen if I can get rid of this n plus 1. So I'm going to go ahead and do that. We'll do a substitution. How about s? So s is going to be equal to u times n plus 1. That way I can replace e to the negative u times n plus 1 with e to the negative s. Okay, so let's take the derivative of both sides. I'm just going to get ds equals n plus 1 times du, right? The u goes away. And I can now rewrite my integral. So I'm going from 0 to infinity still. This isn't going to change the 0 to infinity aspect of all of this. E to the negative s. Now u, I'm going to take the s and divide it by n plus 1. So this is going to be s over n plus 1 all to the power of n. And then the du is going to be replaced by ds divided by n plus 1. So I'm going to have ds divided by n plus 1, and this is all over n factorial. Now I'm going to go ahead and pull some things out. I'm going to pull out the n factorial, and 1 over n plus 1 to the power n times 1 over n plus 1 is going to give me 1 over n plus 1 to the power of n plus 1, right? N, and then this is all to the power of 1, so n plus 1. And then I have my integral from 0 to infinity of e to the negative s times s to the power of n, and you can see it looks quite nice right here. And in fact, this thing is exactly equal to n factorial, so this thing is going to cancel out with this thing. How can we show that this thing is equal to n factorial? Well, I won't do like a total proof, but I will show you. So basically, you just want to do integration by parts. So remember, integration by parts, ultraviolet VDU, ultraviolet video. So the way I'm going to do it is I'm just going to write my derivative column on this side and my integral column on that. That's supposed to be an s. So the derivative of this is going to be n times s to the n minus 1. The integral of this is going to be negative e to the negative s, right? I'll just rewrite that. That's e to the negative s. That looks a little better. Now I can do the diagonal. The first diagonal is associated with a positive sign, so I'm going to get s to the power n, e to the negative s, evaluated with the bounds of integration, like that. And then I'm going to do a horizontal line because I want to do an integral, and this is going to have to be a negative sign. So negative times a negative is a positive. The n I'll put on the outside, and then I'm going to have the integral 0 to infinity of e to the negative s times s to the n minus 1. So effectively what I've done here is I've taken the exponent of n and replaced it with an n minus 1, but this n has popped out to the outside. It's almost like I've pulled the n out here, and this has become an n minus 1. Now what about this part? If I plug in infinity here, e to the negative infinity is going to make this whole thing 0. If I plug in 0, well, 0 to the power n is 0. 0 times something is 0. So in fact, this all just goes away. So this shows a little bit of a recurrence pattern. So in fact, I pulled out the n to make this an n minus 1. And then I could pull out the n minus 1 to make this an n minus 2. And then I could pull out the n minus 2 in order to make this an n minus 3, and then I can keep doing that all the way down until I basically like vanish the whole thing. So if I look at this integral here, where it's just s instead of s to the power of like n being something not equal to 1, you can evaluate this with integration by parts and it just comes out to 1. So this thing here would be the one at the end here. So this thing is in fact just equal to n factorial, which is going to cancel out with that n factorial, leaving us with just this part. Remember in the beginning that I had a summation sign on the outside that I just stopped writing, but I'm going to go ahead and write it now. So now this is what we have. This is the whole thing. We've reduced things quite a lot, right? Now I could also write this as, you know, n plus 1 to the power of negative n plus 1. Why not? Why not write it that way? And then what I can do is I can just change the lower bound to an n equals 1. But to compensate for that, I'm going to have to reduce these by 1. So now n plus 1 minus 1 just gives us n, and this n plus 1 minus 1 just gives us n. And this is what we were looking for. So this whole thing is equal to the integral from 0 to 1, x to the negative x dx. It's a very cool identity. It's called the Sophomore's Dream. And yeah, let me know what you think. Let me know if you have any questions. Yeah, I hope you found it fun. I hope you found it interesting. And take care. Have a good one.